now. Okay, so this is lecture number 8 under air conditioning systems and control. So you can refer to the study guide, the second study guide. So we have 2 files. Second file is on air conditioning systems and control. And today we are going to cover variable air volume system. So obviously, the background is the same as lecture number 7. For a typical air conditioning system, if you look at the air side, you will find that the load actually will change with time, location, and personal needs. So at the beginning of lecture number 6, we discussed how you can categorize your space into different zonings. And for each zone, and then after that, your next step is to choose a suitable air conditioning system. So as the in controlling the air conditioning systems, the aim of this the control is to maintain a certain temperature and humidity indoors. And in order to control that, we can only control the supply temperature or supply flow rate. If you look at the equation in the right-hand side, this equation is on the sensible heat, how you can calculate the sensible load of a HVAC system. So you can see that it's related to the density of the air, the supply flow rate, and the specific heat of the air, and TR is our aimed control temperature for this room or for this enclosed environment, and TS is our supply temperature. So by looking at this equation, we found that this value, density, and the specific heat of air are actually related to the properties of air, so you cannot change that. And the T sub R is what we would like to achieve. So this value is also fixed once you have fixed all the design conditions. And so we are left with V sub S and T sub S. And V sub S is corresponding to supply flow rate, and T sub S is corresponding to supply temperature. So in other words, that means in order to control or in order to maintain a design temperature or humidity ratio in indoor space, what you can control for the air conditioning system are supply temperature and supply flow rate. So according to that, we did discuss the constant air volume system or CAV system in lecture number 7, and we also discussed the fan coil system. So a CAV system is one category of all air system, and for CAV system, you can see that it's constant air volume, so that means its supply flow rate is maintained the same throughout the air handling unit. Whereas for VAV system, we can actually control the supply air volume, and the VAV system, its control principle and application is what we are going to cover today. Okay, so first of all, we will be looking at the air handling unit of a VV system. We can see that it's quite similar to the air handling unit of CAV system. The fresh air first was induced into the air handling unit, and we have a filter to, first of all, clean the outside air, and then the outside air will mix with the return air. So when it mixed with the return air, it will go through a preheat coil, which will work in winter. And then it goes through another filter, and the air is further cleaned. After that, we get a clean air, and then it will go through a cooling coil and a reheat coil. So by controlling the cooling coil and the reheat coil, we can control or we can condition the air to the state to a suitable state. And then after the fan induced power, the conditioned air will be supplied to the system, to the room. So a major difference between the air handling unit of a VAV system and the CAV system is the fan here. So for VAV system, normally this fan is variable speed. So that means you can actually change the speed of the fan, and that will result in a change of the air volume in the system. Okay, so first of all, we will be looking at the basic control principle. For a single zone, that is conditioned by the VAV system. So you can see that we have return duct and we have supply duct. And for the return air, this sensor is actually connected to a controller, and the controller is actually connected to a fan speed controller. And the fan speed controller will send signal to the frequency inverter where you can change the power supply to the fan. So that means the supply air flow rate can be varied to maintain the room temperature. And apart from this return air temperature sensor, we also have another supply air temperature sensor. So for the supply air temperature sensor is connected to a supply temperature controller, and this temperature controller can control the chilled water flow rate by connecting to a chilled water control valve. So by regulating the chilled water flow rate, the supply air temperature is kept constant. So this is the basic control principle of a VAV system. So you can see that obviously, first of all, the volume of the air will change. And you may ask why we will need to control or control the supply air temperature, as obviously we only aim to control the supply air flow rate. So when you change the supply air flow rate, the mass flow rate of the air going through, for example, goes through this cooling coil will change. And inside or at this cooling coil, as we have learned in, I think, lecture number 2, the moist air actually will exchange heat with the cooling coil, or more specifically, with the chilled water that's flowing through the cooling coil. So for example, when the fan is working at a speed and the air supply air flow rate is 2 cubic meter per second, and our design supply air temperature is 14 degrees, the chilled water temperature is maintained at a certain temperature and at a certain flow rate. When the cooling load of the room reduces, then the return air temperature will increase. And this temperature sensor will capture that increase, and it will send the signal to the fan speed controller to lower the fan power frequency. And then maybe the, for example, the flow rate of the air is reduced from 2 cubic meter to 1 cubic meter. And then only by changing this flow rate of the air and by maintaining the temperature of the chilled water and flow rate of the chilled water, then we can see that in analyzing the energy balance here, the load of the coil actually will be maintained more or less the same. And then since the airflow rate is reduced, then we will know that the temperature difference between the return air and the supply air will be increased. So that means if the flow rate here is maintained the same and the temperature of the chilled water is maintained the same, when you reduce the airflow rate, then your supply air temperature will be dropped. For example, it will be dropped from 14 degrees to only 12 degrees. And then when you supply that temperature to the air, your conditioned room cannot be maintained at your design temperature. So in order to avoid this situation, what we do is we will install a sensor here also at the supply air, and then the sensor will be connected to a temperature controller, and this temperature controller will further control the flow rate of the chilled water. And when the load varies, by maintaining this supply air temperature, we can actually only change the fan speed to further change the air volume or airflow rate of the system. So this is the basic control principle of a single zone of a VV system. And in this controlling strategy, supply air temperature is kept constant and the supply air flow rate is varied. So this is how you can do that for as a basic control principle, and we will be looking at other control principles, more complex principles. So the previous slide shows the basic control principle for a single zone system, and then now we are going to talk about the basic principle for multi-zones as we install this VV system to, for example, office buildings. Normally, or there is a very prevalent design is we use VV box for each and every room. So for multi-zone, each zone is installed with a VV box, and the VV box is shown here. And I'm going to get to the schematic of the VV box later. And since it's multi-zone system, so each zone is supplied by this terminal device, which is the VAV box. And you can actually realize temperature control of each zone. And for that means the return air temperature. You can actually control the temperature inside the room. And the airflow to each zone is controlled by a zone thermostat to open or close the VAV box damper. So this is how it looks like. And we have preconditioned supply air supplying into this small VAV box. And the VAV box is installed in each of the zone. If we're talking about office buildings, then it's installed in each of the office room. And now we can see that at this VAV box, we have a damper inside. And by controlling the damper, we can actually control the temperature, we can actually control the flow rate of the VAV box. So one major difference between this VAV box and our previous basic control of a single zone is for this single zone control, we are controlling the airflow rate obviously in the air handling unit, and also by controlling the airflow rate here, it will affect the supply air temperature, and this is the reason why we will also connect a supply temperature controller. But here in the VAV box, the air here is preconditioned by the primary air handling unit, and by controlling the damper, it will only affect the airflow rate. And by changing the airflow rate, the temperature of the supply air will not be affected. So here we can see that only one temperature controller is needed. So this temperature controller is connected to a temperature sensor that is installed in the zone or installed in the office room. And then the controller will send signal to the actuator, and the actuator will control the position of the damper. And then our supply air flow rate for each room or for each zone can be controlled. Okay, so this slide is a further illustration of the control of VAV box. So you can see that for the VAV box, we have air from the primary air handling unit. And then the VAV box will supply air directly to the room. We have a control input here, which is the censored room temperature, and we compare that to the set point room temperature. For example, if our set point room temperature is 24 degrees, and we found that the actual room temperature is 26 degrees, and then this controller here will capture the signal. So the control input is the difference between the two temperatures, the set point temperature and the actual temperature, and then the controller will output send the signal or send the control output. And the control output is the actual flow rate. So that means when it actually received the signal, it will control the mass flow rate controller. And then for the mass flow rate controller, the control input is the actual mass flow rate and the set point mass flow rate. So what you do is you will calculate a set point supply air mass flow rate by measuring the actual room temperature. And then with the input of the mass flow rate arrow, the mass flow rate controller will output the damper opening. So this is the signal to let the damper open up or close down. So this is a more illustrated example of the control of a VAV box. Okay, then we will be moving on to the multi-zone basic control system, basic control principle. And this control strategy is called dual static pressure control. So in this multi-zone VAV system, the fan speed is regulated to maintain a static pressure set point. And so there will be adequate but little pressure fluctuation at the VAV box inlet. So you can see that for this VAV system, we have a primary air handling unit, and this primary air handling unit will supply air directly to multiple VAV boxes, and the VAV boxes will be controlled as illustrated in slide number 7 and slide number 8. So you can see that in controlling the single VAV system, what we do is we control the position of the damper. However, when you control the position of the damper, you are actually adding resistance to the duct. So there might be a scenario where the resistance of the duct is too large that the air cannot, the airflow rate of a single VAV box can be zero sometimes. So in order to avoid that situation, what we do is we install a pressure sensor here. And the pressure sensor is connected to a fan speed controller where you can actually control the fan power. So by maintaining static pressure here larger than the, for example, pressure at the outlet, then the air can be successfully flowing from a high pressure position, which is at the air handling unit, to a low pressure position, which is at the specific zone here. So this is what it means by dual static pressure control. And this is a further illustration on the realization of the dual static pressure control. So you can see that we have a primary air handling unit supplying air, for example, to these two zones. So we have single zone VAV box control for each of the zone. And then we have a primary pressure sensor here. So the temperature sensor also will be installed at the outlet of the air handling unit, where it will be connected to a controller that can control the flow rate of the chilled water. So the temperature, supply air temperature is kept unchanged. And when, for example, when the supply air volume to any zone controlled by the damper here is reduced, then this pressure will rise. And when the pressure rises, the flow will be flowing to here, but not to the designed zone 1 or zone 2. So the fan speed will be reduced to track the set point of the pressure here. So this is how a further illustration of this dual static pressure control. Okay, to better illustrate that, we can see that when the fan speed should be reduced, in conclusion, should be reduced when a VAV box damper is closed down. And if we look at the pressure, when the VV damper is closed down, then the static pressure will be increased. And then the controller, the sense controller will reduce the fan speed, and then the static pressure will be reduced again. So the static pressure, therefore, the static pressure is a good indicator to let the fan stay at a correct speed. And control the fan speed is based on the error between the static pressure set point and the supply air static pressure measured by the sensor. So similarly, if the measured static pressure is higher than the set point, then the input of the controller, which is the error between the sensor, measured pressure and the set point pressure, will send the signal to decrease the fan speed. In another scenario, if the measured static pressure is lower than the set point, then the signal will be sent to the fan motor to increase the fan speed. And also, the return air flow rate should be equal to the supply air flow rate. So this is the reason why we also have sensors at the return fan and at the supply fan to actually measure the actual supply airflow rate and return airflow rate. And the controller will take the two measured results of the two sensors, and then we can see that the input is, we have the arrow. So this sensor send out the signal to the controller, and this sensor also send the signal to the controller. And this is the input of the controller. And the output of the controller is the motor of the return fan. So M1 is the supply airflow rate by the sensor, and M3 is the return airflow rate by the sensor. So in some of the systems, we have a return fan, also have a return fan. So the return fan speed for the VV system will also need to be controlled. And if M3, or return airflow rate, is higher than the supply airflow rate, and then the signal will be sent to the controller here to decrease the return fan speed. And if the return fan flow rate is lower than the supply air flow rate, then the signal of the controller will be sent to the return fan motor to increase the fan speed until the measured supply airflow rate and the return airflow rate is equal to each other. Okay, so now we will be looking at the psychrometric process of a VV system under a basic control principle for a single zone. The red lines here illustrates the full load cycle. So this cycle is actually the same as the CAV system. And then we will be looking at what this psychrometric process looks like when the VAV system is working under partial load. So when it's working under partial load, obviously, first of all, the outside air will remain the same. And then the coil actually and the supply air temperature will also be maintained at the same state. And then if the room sensible heat ratio changes, for example, here for this partial load, the I think here only the sensible load is reduced and the latent load is remain the same. So in this scenario, in this partial load scenario, the SHR line is changed. So this is why our supply air state will remain the same, and our SR line will not be the same. However, this VV system is under temperature control, so the return air temperature will be the same. And the only difference there might exist is the humidity ratio of the return air. So that means in a VV system, the changes of the room relative humidity will be small. And this change in room relative humidity actually depends on the degree of variation of the room SHR line or the room sensible heat ratio. Okay. So from our previous contents, we have found that the VAV system actually relies on the control of the fan speed. And the control of the fan speed actually relies on the by controlling the fan speed, the airflow rate of the fan-powered airflow rate will change. So next several slides, we will discuss the relation between the fan power and the speed. So this figure shows the relation between the fan power and the flow rate. So you can see that this is you can actually change the flow rate or change the fan power by damper control, as illustrated by this line, or by inlet guide vane, as illustrated by this line, or you can change the fan power and the flow rate by variable speed, as illustrated by this line. So we'll be looking at variable speed because this is the way we control the fan speed in VAV system. The higher of the variables of the speed, the higher the fan power and the corresponding flow rate is. And we found that the relation between the fan power and the speed is that the fan power is positively related to the exponent of 3 for the speed. So that means if the speed is changed from 1 to 2, increased by 100%, our fan power will be increased by 700%. So that because 2 to the order of 3 is 8. So our fan power will be 8 times of the original fan power. And as you can see, the fan power of the variable speed control compared with damper control and the inlet guide vane at the same flow rate, for example, at this flow rate here, the corresponding fan power by damper control is the highest, and then followed by the corresponding fan power of the inlet guide vane control. And the variable speed control will consume the lowest fan power. So that means the VAV system actually, by installing variable speed control, it will allow saving in fan power. Okay, so it's 9:16 now, and we will have a short break, and we'll resume our lecture at 9:31. I'm going to stop recording.